Have you ever wondered how the GPS finds our location and coordinates? Hi, I'm Maham, and today I'm going to show you how the GPS system linearizes information given by satellites with a Taylor series expansion in order to find the coordinates. Typically, at least 4 satellites are used. The raw data given by satellites are times of transmission and times of reception. There are also clock errors in the satellites and receivers, which are estimated by the satellites and receivers themselves. These times of transmission and reception are arranged in an equation that calculates a pseudo-range, or distance between the satellite and receiver, including clock error. This equation is derived from the speed formula, in which distance is the only unknown because the speed of radio signals is just the speed of light. We can make this equation equivalent to the distance equation. The following equation represents a pseudo-range of each satellite. Each pseudo-range equation forms a circle. Then, you'll have a system of 4 equations because we have 4 satellites. This is how these equations and their solution look. The typical and arguably most efficient way to solve a system of equations is through a matrix. But as you can see, this requires all the terms to be linear. So how do we linearize these equations? This can be done through a Taylor series expansion. What does a Taylor series expansion do? A Taylor series is an infinite sum of terms that are equivalent to some function. This expansion uses the derivatives of the function to provide a sum of terms that becomes closer and closer to the given function when added together. An important note is that the Taylor series is approximated around a chosen point. This means the function being created by the sum of terms doesn't have to start at the origin and could potentially start here or here. As you can see in this drawing, the first function created in the Taylor series expansion is a line. This means there must be linear terms in the Taylor series. Sure enough, the first 2 terms are linear. Graphing these 2 terms creates a line that touches our original nonlinear satellite given polynomial and is a rough linear approximation of this function. But knowing these 2 terms is not enough to fully linearize the data. What point do we approximate around? GPS receivers approximate around any set of values that satisfies this pseudo-range equation. Thus, any set of values that are found on this circle can be used. We don't want to use 0 because, as you can see, the farther the value is from the approximated point, the less accurate the line is. That is why we approximate using known values that are somewhat close to the point we are looking for. The satellite receiver plugs in each pseudo-range equation and one set of values that satisfies it into the Taylor expansion's first 2 terms. This results in 4 linear equations that can be solved by matrix manipulation in order to give us the coordinates of the GPS receiver.